All right, let's try another one of these bad boys. Let's calculate the enthalpy change for the reaction of solid ammonium chloride and solid barium hydroxide. We're going to do this one in class. It's really interesting. Blast from the past. Let's write this balanced equation. Hello, Chapter 4. We should know some common polyatomic ions for the AP test. Ammonium would be one. Ammonium chloride. Barium hydroxide. Hydroxide would be another. Plus 2 minus 1. There we go. Okay, so this kind of looks like a double replacement maybe. I would have some barium chloride. And then I got to check those charges because I made a new compound. And some ammonium hydroxide. Plus 1 minus 1. And then we got to balance this sucker. 2 chlorines. 2 ammoniums. Perfect. I need 2 hydroxide anyway. So you might think that this looks great and I'm done. But then again, Chapter 4 will haunt you forever. There are certain products that will further decompose. Common ones are things like that hydrogen carbonate. That's come up a couple times. Hydrogen carbonate will further decompose to form water and carbon dioxide. And then they might say, like, what is a common test for carbon dioxide? And we'd say, well, carbon dioxide should extinguish like a glowing wood splint. You light a wood splint on fire, and if you put the end of it in your test tube or beaker or whatever, that carbon dioxide should extinguish the flame. It's this guy that we're concerned with in our reaction here. Ammonium hydroxide will further decompose into ammonia gas and then just liquid water. Water in the liquid phase. And we could still put those coefficients in, so it wasn't a total loss. Like I usually do, just balance the equation right away, but then I keep my eye out for some of those products that will further decompose. Those are probably your best 2 examples, ammonium hydroxide and hydrogen carbonate. Now if they said, describe a test that could confirm the ammonia gas. We'll do this one in the lab and you'll definitely smell it. There's always somebody that just like takes a big whiff of it. Maybe like gently waft it. Then they like water their eyes and they're ready to pass out. That's some strong stuff. The odor is a good confirmation. We also recognize NH3 ammonia now as a weak base. So you could take a pH strip, like a piece of pH paper, maybe just kind of get it wet, and then hold that in the mouth of your test tube or in your beaker, and that ammonia gas should show a basic color on your pH strip or your pH paper. It should turn it blue. That'd be another good confirmation of the ammonia gas. Okay, so that's our final balanced equation. And now let's calculate the energy change for this sucker. So we're going products minus reactants. Now my products, I have 3 products. I have that 1 mole of barium chloride, negative 860.6. They're all in kilojoules. I'll put kilojoules in at the end. And again, that's the barium chloride. Cool. Oopsie, I got more of them. Barium chloride. I got to add the ammonia. There are 2 moles of ammonia gas. Negative 46.1. So there's the NH3 ammonia. Plus the 2 moles of water in the liquid phase, negative 286.0. There, now I'm done. That's the water. There's all of my products, and then I'm going to subtract the energy change from all of my reactants. I'm going to have 2 of those ammonium chlorides. Ammonium chloride, negative 314.4. That's my ammonium chloride. And then I just have the barium hydroxide, negative 998.2. And that's my barium hydroxide. Again, I think the key to these is just staying organized. The common mistakes, people go reactants minus products. They just want to get so excited about that ammonium chloride, and they start with that, and they realize, oh dang, it was products minus reactants. Or they'll forget the coefficients from the balanced equation. In that chart, the enthalpy of formation values are kilojoules per 1 mole. In the balanced equation, we may have more than 1 mole. Or it is possible that you have like half a mole, and then we could multiply by half. Okay, so now again, you could just plug all this in your calculator. Go nuts if you want to. Sometimes I kind of like to just simplify these expressions. So if I plug this in my calculator, negative 860 plus 2 times negative 46.1 plus 2 times the negative 286. Now this whole group gives me negative 1,524.2 minus this whole group 2 times negative 314.4 plus the negative 998.2. So this grouping is about negative 1,627. Obviously, you don't have to do that. When they say show work, just show all of this. Show the numbers that you used. What did you add? What did you subtract? All that good stuff. But I don't know. This seems to help me. Sometimes I'll miss like, oh, dang, that was minus negative or something like that. And if I plug this into my calculator, I'm going to get endothermic by 102.8 kilojoules. There, I'll put the kilojoules in. Again, with these thermal problems, you always have to indicate the direction of the energy flow. You could do that by either saying it's positive 102.8, or you could write the word absorbed. You could say 102.8 kilojoules absorbed. If you leave the positive out, I guess technically it's assumed then that you mean that it's endothermic. If it was exothermic, I would need to either indicate that the delta H is negative or that it's energy released. This one's kind of interesting. It's energy absorbed. It's going to absorb the energy from its surroundings. So like the outside of the beaker is going to get really cold, which feels, it's kind of strange. It's cold because this reaction itself is absorbing energy from whatever it's surrounding. So it's going to be like the air, the beaker, all that good stuff. So there we got an endothermic. Let's try one more of these puppies. Again, you'll just be masters of this enthalpy of formation. Oh dang, they didn't give us the balanced equation again. Fine, we can deal with it. The standard enthalpy of combustion for 1 mole of ethane. Ethane is that C2H6. Combustion means we're burning it in the presence of oxygen. And we always produce carbon dioxide and water. I'm expecting this to be exothermic overall. Combustions mean something is burning. There should be energy released. We need to balance this thing. A lot of people will balance this and they get started and they'll say like, gosh, this is so easy. 2 carbons, 2 carbons. 6 hydrogen. 3 times 2 is 6. And then they'll get kind of stuck because now they've got 4 oxygen and 3 oxygen. And they'll say, well, how do I get 7 oxygen over on this reactant side? You have a few options at this point. I usually say, whatever I do to this oxygen, it's going to give me even numbers. And it's this 3 waters that's making it odd on the product side. Double it. Try doubling it. Now I get we're going to have to go back and double this. So we have 12 hydrogen. And now we're going to have to make this 4 carbon. But now here I have 4 times 2 for 8 and 6. I can do 7 times 2 for 14 oxygen. Maybe that's kind of the most simple way of balancing that equation. Find the oddball and double it. And then you should be able to balance the oxygen with the O2. Okay, so let's use this as is. Let's get products minus reactants going. products. Okay. I have 4 times that carbon dioxide in the gas phase. Negative 393.5, and it would be kilojoules. That's my 4 carbon dioxide plus the water. And we mentioned that if you're doing these in the homework or you have to look the numbers up, just be a little careful. Sometimes charts will give water in both the gas and liquid phase. So you kind of have to think like which one would be used here. And we're writing the equation ourselves, but a combustion should be exothermic, and often that water comes off as water vapor. I mean, rarely are you doing a combustion where you'll see liquid water formed. So this would be, I should put the 6 in first. The 6 waters in the liquid phase, negative 241.8. There we go. Now that's the water. Products minus reactants. Let's get the reactants. I'm going to have 2 ethane, negative 84.7. That's for the C2H6. Plus 7 times nothing, 0.0. That's for the oxygen, the diatomic oxygen in the gas phase. That's just its elemental form. So it's not listed on the chart because I would be expected to know that elemental oxygen is naturally occurring. Its enthalpy of formation value is 0. All right, so I kind of like to simplify these. So I'm going to plug this in 4 times negative 393.5 plus 6 times the water, negative 241.8, negative 3024.8 minus 2 times negative 84.7, negative 169.4. Then I'm not going to miss like this whole minus negative or something kind of simple like that. Delta H. Yep, exactly what I expected. Negative 850. Well, it's 55.4 if we're not concerned with sig figs, which for now let's plug that in. Kilojoules. Okay, so again, this was super easy and we think we're done. Just be a little bit careful. They want the enthalpy of combustion for 1 mole of ethane. We calculated the enthalpy of combustion for this reaction as is written, with 2 moles of ethane. And that's pretty common, especially with a combustion. They might say the standard molar enthalpy of combustion. That means per 1 mole. Well, this is for 2 moles. Well, that's not such a big deal. All we got to do then is divide this by 2. And then I'll get my final answer. Negative 1,427.7. That would be kilojoules per 1 mole. That's the final answer I want. So just be a little careful how they're wording those. Okay, excellent. So again, there's only a few little things you got to watch out for, but otherwise these are very straightforward. Check out this last one. Compare the enthalpy value calculated above to the value obtained using bond energy data. Woohoo! Blast from the past, chapter 8. Excellent. Do you remember this kind of data? Bonds broken minus bonds formed. Oh, yeah. So we have the same equation. Let's say we got the 2C2H6 plus the 7 oxygen. Da-da-da. And then we got the 4 carbon dioxide and the 6 waters. And then we eventually use something like delta H equals total energy of the bonds broken minus the total energy of the bonds formed This was just another way of calculating the energy change from a chemical reaction. We should get the same answer. So how do you know which one to do on the AP test? It just depends on what kind of data they give you. If they give you these bond energies, then we're going bonds broken minus bonds formed. If they give me the enthalpy of formation data, then I'm going products minus reactants. Now with these guys, remember how we kind of said that sometimes it helps to draw the Lewis structure? So if I were to draw this little puppy, I'm going to have 2 carbons. Carbon always needs 4 bonds. So here are my 6 hydrogens. Cute. Hopefully we remember that O2 oxygen is a double bond. And then the other spots are lone pairs. You might recall that carbon dioxide is also double bonds. And I mean, you might be good enough that you kind of remember that right away. And then we kind of write them like that. Or maybe you kind of have to link up the dots. And you say, well, carbon has 4 valence electrons. Each oxygen has 2 singles and 2 pairs. So I can connect the dots twice. And then I can do kind of the same thing with the other oxygen. Connect the single dots. Well, what do you know? 2 double bonds. But again, if you're so good that you remember that it's 2 double bonds, you can write it like the first option. And then water. Water is that bent-looking structure with the 2 lone pairs on the oxygen. Single bonds. All right, so let's say we do bonds broken. Here they are, bonds broken. We're going to need to break. Oh, interesting. Okay, so there's 1 carbon-carbon bond in the middle. I need to break that 1 carbon-carbon bond. But in my balanced equation, I have 2 times that. I have 2 moles. So at some point, we're going to need to break 2 carbon-carbon single bonds. So we're going to take 2 times carbon-carbon single. 347.0. And again, these are all kilojoules. So you have to kind of watch the balanced equation to check the ratios. Then we need to break these 6 carbon hydrogen bonds, but I need to multiply that by 2, so there's really 12 of them. Carbon hydrogen bonds. 12 times, let's see, 414.0. And then I've got the 7 oxygen-oxygen doubles. 7 times 498.4. Okay, so we're going to plug all that good stuff in our calculator. And there's the energy required to break the bonds on the reactant side. So that's going to be 9,148. Excellent. Kilojoules. And now we do the same thing to the bonds formed. On the product side, we're going to form 2 carbon-oxygen doubles, but then we need to multiply by 4, so there's actually 8 of them. 8 carbon-oxygen doubles. 8 times 804.0. And then I've got 2 of these oxygen-hydrogen singles times 6 for 12. Oxygen-hydrogen singles. 12 times 464. Excellent. So plug all that in for 12,000 joules. Okay, so again, here's kind of what we said. Here's where this equation comes from. Bonds broken minus bonds formed. So you're going to have to add energy to break the bonds on the reactant side. So we're going to have to add 9,148 kilojoules. Whoopsie, I should put that in as kilojoules. To break the bonds on the reactant side. Now technically, this 12,000, that's the amount of energy I would have to add to break the bonds on the product side, but I'm forming these bonds. Well, if I form the bonds, I'm going to release that much energy. 12,000 kilojoules. I'm releasing more energy when I form the new bonds than it takes me to break the bonds on the reactant side. So this should still come out to be exothermic. 2,000, like approximately 852. Now again, that's for this reaction as is written with the 2,746 ratio. If we go back and compare to the last one, what do you know? Like, it's almost exactly the same. This negative 2,800 kilojoules was for the 2,746 ratio. If they asked me kilojoules per 1 mole, I would do the same thing and divide by 2. And then I would get something real similar, like approximately 1,400 kilojoules per 1 mole. These are two methods of calculating the energy change for a chemical reaction. It just depends on what kind of data you have as to which way you're going to attack the problem. But again, what a good review from Chapter 8.